I'm going to show you how the hydrostatic pressure equation is derived. We've got to pull a couple of different basic physics equations from our arsenal, one of which is the general pressure equation. Pressure equals force over area. We're going to zoom in and think about what this really means. Force is measured in newtons. Area is measured in meters squared. You take a newton, take a meter squared, and put them in their proper positions, and you get a newton per meter squared, which is really just a Pascal. And that is the unit for pressure that you can think of most commonly as far as the derived SI unit. Additionally, we should remember that force equals mass times acceleration. And since we're understanding acceleration to be really the acceleration of gravity, the constant acceleration of gravity, we're going to replace A with G for the acceleration of gravity. So force, really weight, equals mass times the acceleration of gravity. Now we're going to substitute mg, where F is, in the pressure equation in the first step of our derivation. Pressure equals mass times gravity divided by area. Now we must think of the density equation. Density, which we can denote using the Greek symbol rho, equals mass divided by volume. The unit that is used for mass is the kilogram. The unit that is used for volume is the cubic meter. Therefore, the derived SI unit for density would be kilograms per cubic meter. It is important when you're solving these equations to make sure that the density of your fluid, of your non-compressible fluid, which would be the liquid, is in kilograms per cubic meter and not grams per cubic centimeter or grams per milliliter. We're going to take the density equation and solve for m, which will give us that mass is equal to the density times the volume. Knowing this, we can substitute rho times v, which is density times volume, in for where m is here. And that gives us our third step of our derivation. Pressure equals the density times the volume times the acceleration of gravity divided by area. We have to think back to what volume really is. A three-dimensional object has length, width, and height. This prismatic object, and it also works for cylindrical objects, shows us that volume is length times width times height. So length times width is really just area. So length times width is the area, which we can abbreviate with capital A, and it's still multiplied by height. Area is two-dimensional, height is one-dimensional, so area brought to the third dimension by multiplying by height gives us our volume. In reality, and more simplified, volume is equal to area times height. And that is what we're going to substitute into our current derivation step. Density times area times height times the acceleration of gravity divided by area as the part of the original pressure equals force over area equation will lend most of us to see right now the area will cancel out. That means that the pressure at a certain depth, pressure as a function of height below, or depth below, the surface is equal to the density times acceleration of gravity times height. Of course, I can switch around rho, g, and h because they're all multiplied together. However, let's take a look at the schematic. In something that is open to the environment or open to the air, the pressure on something at this depth of h is not just due to the fluid or the liquid that it is in. It is also due to the atmosphere pushing above it. Do not forget that there is atmospheric pressure pushing along this area. We're going to call that atmospheric pressure P sub 0 or P sub naught. Atmospheric pressure in pascals must be added to the rho g h equation to determine the true pressure at a certain depth. Now we're going to check our units. First, reminding ourselves that pressure is a Pascal, which is a Newton per meter squared. Let's see how the other variables are going to play out. The units for density we discussed at the top would be kilograms per cubic meter. We are multiplying this by the acceleration of gravity, which is a meter per second squared. And that is being multiplied by the depth or height below, which would be meters. Multiplying these all out, we get kilograms times square meters divided by cubic meters times square seconds. It is obvious that what a Pascal is on the left does not appear to be what we discovered on the right. So let's think about what a Newton truly is. Remember that newtons are what force is measured in. So force equals mass times acceleration, or mass times acceleration of gravity. This is the basic way to say it, F equals ma. And let's think about what those units are. We know that mass is kilograms, and it is being multiplied by acceleration of gravity, which is meters per second squared. So a Newton is a kilogram times a meter divided by square seconds. Let's take what we know as a Newton and divide it by meters squared. Kilograms times meters divided by seconds squared divided by meters squared is, and think back to the math that you remember from algebra, a fraction divided by another fraction is really just the numerator fraction multiplied by the inverse of the denominator fraction. So I'm going to get rid of the meters squared over 1 and multiply it as a 1 over meters squared. We're going to squish all of this together and make it kilograms times meters divided by meters squared times seconds squared. There is one dimension of a meter on the top, and there are two dimensions of a meter on the bottom. One will cancel out, giving us our final units of kilograms per meters times seconds squared. This is equivalent to this because both are simplified to kilograms times meters squared divided by meters cubed times square meters, which is really, finally, kilograms per meters times second squared. They are a match because this is what a Pascal really is. That is all for this derivation video, and happy studying.